Hi, everyone. My name is Ka. I'm a software engineer at Pinterest. Today, this talk is about our new graph service. We call it PinGraph. So graph service has been a pretty important part as a storage platform at Pinterest for many years. And recently, we built a new version on top of TiDB. And we are very happy to have this opportunity to share our journeys here. So a quick agenda for today. We are going to do a quick introduction, and we're going to share some background and histories about graph service at Pinterest, our challenges over the years about our old system, then move on to the motivations and share some design details about PinGraph. In the end, we're going to share the results and hopefully leave some time for Q&A. So without further ado, let's get started. In case anyone is not super familiar with us, Pinterest is a visual discovery engine for finding ideas like recipes, home, and style inspiration. So our mission is to bring everyone the inspiration to create a life they love. We just reached over 500 million monthly active users this year, which is a pretty big milestone for the entire company. And our team is called a storage service, which is part of the online systems under the data eng org within Pinterest. So as the name suggested, we own a few data storage layer at Pinterest. For example, the structured data store services, or SDS, which is our unified framework to support multi-data model and multiple data stores. And in fact, the PinGraph system we are going to talk about today is actually one of the data model built on top of SDS. And we're going to share more relationship between PinGraph and the SDS later. We also own the existing graph service and our edge-based cluster today as well. So a bit about background and histories about our existing graph service. We call it Zen internally. Zen was launched back in 2014 by Pinterest. It was inspired by Facebook Tao to provide graph-like data models such as node and edge. And each node and edge can have properties inside them. Basically, every property is a key value pair. And currently, Zen was implemented on top of either Edge-based and the MySQL backend. And we have a built-in caching layer built on top of MinCached. Over the years, Zen has been the primarily data service at Pinterest to support business growth. Today, there is over 100 plus use cases on Zen, over 10 plus clusters. Some of them are serving super mission critical features for Pinterest, such as a follower service, notifications, shuffles, which is another app launched by Pinterest about 2 years ago, and also user messages and smart feed as well. So today, the total data size served by Zen is over 1.5 petabytes, and the total QPS is about 8 million across all the clusters. I think the biggest cluster is serving about 1.5 million QPS from a single cluster, which is a pretty big system for us. Similar to Facebook Tao, it's worth mentioning that Zen is not a general graph database. The purpose of building Zen is more like to providing an abstractions of our existing database like Edge-based and MySQL, so that we can simplify the product engineer for their development. So today there is no advanced graph algorithms in Zen, such as shortest path or depth first search. The mostly query pattern is like get some nodes by properties, get edges by their properties, and also some from a node and find adjacencies of them. Here's a high-level diagram of Zen. There's an online pass here. As mentioned, it was on top of HBase and MySQL, and the main cache as well. There's also an offline pass on the right. We call it Dr. Zen, which is mainly a MapReduce job to try to fix the data inconsistencies in the system. And speaking of data inconsistency, that's one of the major challenges we've been facing over the years from Zen, and that leads us to our first challenges we are going to talk about. It's weak consistency support in Zen. So the reason Zen has a weak consistent support is because we maintain the secondary index at the application level. So essentially, secondary index is another table, either in HBase or MySQL. For example, we have some source table, we call it node and edge. And there is another unique index table. There's another non-unique index table. So as when a node and the edge is inserted into the system, there could be multiple inserts to multiple tables without any transaction support. Same as rollback. We handle every rollback at the application level in terms of failure. So on the right, it is a high-level diagram of all the operations involved when a single edge is added to the system. Every green box here you can see is either a insert or updates to a specific tables in HBase or MySQL. So as you can imagine, there could be many failure scenarios here and there cause data inconsistency issues. For example, the data could be in the source table, but not in the indexing table, or vice versa. So that's why we have a external MapReduce job, Dr. Zen, as we showed before, that runs once a day, and try to snapshot the source table and the snapshot the indexing table, compare them with each other to see if anything is missing or anything is redundant, then issue the fixing queries to try to fix them. Those fixing queries go through, shared with customer traffic. They go through the same server, adding extra load, consuming extra resources. So all of this not only fragile to break, but also add a lot of maintenance overhead to our team. And the second challenges we've been facing over the years for SAM is the limited query support. To name a few, there is no composite index. So usually, as mentioned, the query pattern is a get nodes and edges by some other property. But in Zen, only one property at a time. So for example, get nodes where this property A equals to something, and also no range query, only equal comparison. We support one hop query. One hop query is starting from a node, find adjacencies from that node. But again, the filtering logic is also pretty limited, one property at a time as well. And the ordering is basically based on the HBase row key. So once the data is there, the order of the data returned to customer cannot be changed on the per request basis. Last challenge is we have a huge tech debt. For example, the code base is 10 years old. And another thing worth mentioning is our HBase and the main cache version is way behind the industry standard, which makes the system less efficient. And all of these challenges makes the system harder and harder to continue evolve and working on to support more business use cases. And that leads us to think about the new graph service on top of TiDB. The reason TiDB, we think TiDB can be a good fit is because multiple reasons. The first and the most important one is the built-in index with strong consistency support. So simplicity is one of the key principles we had in mind to build a new system. So maintaining the secondary index at the application level is definitely something we want to avoid, and also building extra offline jobs to backfill those indexing table or fix any issues in those indexing table. Secondly, TiDB is a distributed SQL databases, which means it not only offers much more query ability from SQL, also we can scale up our clusters much easier without any manual sharding at the application level. That basically, by the way, manual sharding is what we did for SAM MySQL backend in the past. Also, with TiDB's reliable architecture, we are hoping to make our application more efficient and, more importantly, to reduce infra cost for Pinterest. Last but not least, TiDB is open source software. We have extensive communities like this, which we values a lot as well. Here's a high-level diagram of PinGraph, the system. We'll probably go into details of each component later, but on the high level, it's worth mentioning that there is a PinGraph front end and there is a SDS back end. The terminology of front end and back end is from SDS, our new unified framework to support multi-data model. And just to be clear, the front end here is not meant to be any user interface, but instead it's one of the data model on top of SDS. So PinGraph front end is dealing with graph-related logic there. We also have another table front end or table model on top of SDS, but today we are going to focus on the graph world. I think we have other presentations from past years dedicated to SDS as a framework, so please do also check them online. So the way PinGraph front end and the SDS backend communicate with each other is via a SDS universal query language, which is basically an abstraction of SQL. There's another component we call a type schema. We'll dive deep into it later as well. It's basically act as a source of truth of a metadata. So we define node and edges and their properties index in that type schema component. In terms of the internal structure, this is how PinGraph handles requests or the life cycle of requests. So basically, this slide is basically a zooming of the PinGraph front end we see in the previous one. So when zooming into the PinGraph front end, this shows how the request is handled. So basically, every request has to go through a couple of stages before it can reach TiDB. On the top, it's the first is on the top. The request is hitting our handler layer, which is our first stop of our Thrift API. And by the way, every service at Pinterest is using Thrift today. Same with PinGraph as well. And before anything, the request is passed to a validation layer. The main purpose of this validation is try to protect the system and protect the TiDB from some unknown query pattern or some large query pattern. For example, something would cause a full table scam or something like that. So everything, we ensure everything past this validation layer is some query pattern that we are aware of or at least discussed with our customers. So if the request is OK, we further pass the request into a dispatcher layer, which we also call a planner that does the most heavy lifting. The dispatcher layer will choose a strategy to execute this request based on the information in this request itself and some metadata. So the main purpose there is to generate the sequence of steps or the queries appropriate to this request to execute on SDS or TiDB. Things like whether this request needs to be atomic, or whether this request is best effort, or whether it's touching multiple tables and we need to use transactions, or even this request is not going to touch TiDB directly, but instead it's going to send it to some external message queues to execute asynchronously. Those decisions go into these strategies here. You can think of every kind of access pattern is one of the strategy, and if new access pattern comes up, we expand it accordingly. After that, the request is going to translate into SDS universal query language, as mentioned before, and hit the SDS layer. The SDS layer will actually help us with some of the additional functionality, such as rate limiting, caching, and also managing the connection pool to TiDB, and of course, execute the SQL and got the result back to PinGraph. So this is the whole life cycle of each request in the system. After some high-level overview, we are going to jump into some areas to talk about our APIs, type schema, TiDB schema, and our caching layer. So the first is API and query patterns. Basically, our API is built on Thrift, and it's built on basic CRUD operation on our primitive data type, such as get nodes, get edges, get triples. Triple is our internal entity to represent the subject, predicate, object model. If you're familiar with the graph word, it's basically using to query the node adjacencies. So the rule of thumb there is to avoid creating a new API every time when a new query pattern comes up. That's what we did in the past for the older system. So on Zen, there is over like 50 or 60 APIs already. That's hard to maintain. So here, instead, we build our Thrift model to be as extensive as possible to support different query patterns on the platform. So in terms of query pattern, we have get node edge by IDs or get node edges by properties, except this time we support composite index, and ordering is flexible. Range query we also support it, and pagination is out of the box for those range query. We also support one-hop query, which is the most commonly used query pattern we see in the past for graph service. And but again, this the filtering logic is pretty flexible as well. You can start from one node, get outgoing edges, filter some of the properties on the edges, and further filter some of the properties on those target nodes, and combine things together as well. And for the first time, we supported the multi-hop queries. It's still in experimentation phase, and due to it's still an online query, we limited our maximum hops to 3, just to ensure the latency is still reasonable as an online request. Last but not least, similar to Zen, we support efficient query to count how many outgoing edges from a node or how many incoming edges to it. This is a quick case study representing the, just to illustrate more from the query patterns we've seen before. This is a typical user relationship graph. So each node here can be a user. So there is a name, age, etc. As a properties. And each edge can be one of the relationship. Either it's a following relationship or messaging relationship from one user to another user. So when we try to find user connections, we can use some query like this, like start from this node 1, find all the outgoing relationship, where score greater than something. The score is one of the edge property there. And as mentioned, we can combine different properties in the filtering logic. And then further follow the same relationship type with the same criteria, basically to find your friends of friends. So graph service is typically quite useful when customers want to model these nodes separately. Sometimes they want to query these users independently, but in the meantime, they also want to build a relationship between these nodes, whether it's user to user or user to pings or user to comments, etc. So the interface of graph service can help our product engineers to simplify their programming model instead of our customers need to maintain table and come up with SQLs themselves. So next part is the type schema component. Type schema component is a pretty important component in the entire system. And as mentioned before, it's the source of truth of our metadata to define node and edges. So there's a simple example on the right. It's a simple YAML file to define a user node for information like which this user node, which cluster this user node is belong to, owners, and what kind of properties it has, the data type of those properties, and what kind of index we need on which properties. So this simple YAML file is mostly user-facing and created by our customers directly in our version control system. And we decouple this customer-facing YAML from our system configurations that machines understand more. So for example, once this simple YAML is checked in our system, we have a pipeline to automate it into the production configuration, which is more close to TiDB schema. And from there, we orchestrate anything further, whether it's a new TiDB table needs to be created or a new column needs to be added to existing TiDB tables. So the main purpose there is to allow our customers to only deal with node and edges without worrying about any underlying database we are using or dealing with any schema management. The internal pipeline will take care of for our customers. So those type schema eventually will translate into the actual TiDB schemas. So for the TiDB schema, it's also pretty simple. Node and edges are organized into each TiDB table, and a different node can have different TiDB tables to allow those properties to evolve independently. For example, we may have a user node here, so we have a user node ID, username, email, etc. There could be another pings table, for example, our pings node. We are not showing here, but just thinking out loud, the pings node could have property like title, content, metadata, etc. And that's basically another TiDB table we maintain. Similar to edges, the primary key here is from node ID to node ID and properties for that specific edge. The reason we put every property as a separate column is mainly to create index easily and create a composite index. So basically, we leverage TiDB as much as possible instead of building our own pipelines to either populating some indexing table or fixing issues there. And the TiDB is doing the heavy lifting for us there. Lastly, we materialize this edge count table. This is mainly to support queries like how many outgoing edges from this 1, 2, 3, or how many incoming edges to it. So we have many customers need to need such queries in an efficient way. So we cannot do select counts that kind of thing, which is basically too expensive to both our customers and our database as well. So the next part is caching. Other than TiDB, the built-in caching layer is also one of the pretty important part as a storage platform, so that we can help our customers to cache some of the data instead of a customer needs to maintain another cache cluster and do caching and invalidations themselves. So it's worth mentioning that we built a caching component in the SDS layer, which is our unified system, as mentioned before. So this caching layer is not dedicated to PinGraph, but instead it can be reused by both graph model and the table model on SDS. And it's basically more close to the TiDB world. It can cache some rows by primary key and cache some rows by the index as well. It's a look-aside cache if you're curious. So this caching layer is actually help us for some of the read-heavy use cases to save a lot of traffic going into TiDB and save us a lot of resources there as well. And lastly, we want to share some of the very exciting results of this new system. The PinGraph is already productionized within Pinterest, and we've already done a couple migration from old system to PinGraph. And we are seeing tremendous latency improvements. It can be 10 times faster than old one. So there's a quick screenshot showing the P99 latency comparison between Zen and PinGraph. There's a very spiky green line you can see there. It's the P99 latency measured in milliseconds from Zen. And there's a very thin red line under it. It's a P99 latency from PinGraph. It's clearly to tell it is much stable and much better on the new system. We also achieved over 50% of infra cost savings for Pinterest by moving on to TiDB. And now we have a simplified, unified storage offering within the company with the advanced feature to continue support our business to unblock more complex use cases there. In terms of future, first we are going to finish off our migration and deprecate Edgebase to fully adopt TiDB. And secondly, the GQ support is something we're also pretty interested in as well, because it's becoming a standard graph query language in the industry. Right now, as mentioned, everything is on Thrift API, so sometimes it can be quite tedious to compose some of the complex queries there. And GQ is could be our North Star. We are going to build a friendly user interface to boost the customer velocity. And last but not least, we want to continue evolving the system with more graph native features offering. I want to thank the PinCap team for the invitation and also the amazing support along the way to help us build this application. And also thank you, PinGraph team, to build a system from 0 to 1. Our tech leads for the guidance there, and our leadership to support the project. And lastly, I also want to thank our previous leadership, especially Dave, to support the project as well. And also thank all the previous contributors. And yeah, thank you.